In this lab, we will continue with the Alpine Fault data analysis. Let's look at the regions data frame. So regions data frame has 4 columns. Uh, so REGC 2020 underscore V that contains the numeric values. REGC 2020 underscore 2 contains the region, West Coast region, Canterbury, Otago region, Tasman region, Nelson region, Marlborough region, Southland, and the island is South. And geometry is a multi-polygon and it contains more than one polygon in it. So now in the next step, we will dissolve this region's data frame. So yeah, so we will dissolve this region's data frame by island, this South Island, and we'll use the aggregate function sum. So which means that it will merge all these data into one row. So using the aggregation function sum. So this is how we do that. So we pass the command south underscore island equal regions dot dissolve open bracket by equal island. So that's the name of the column, and comma egg function equal sum. And when we display the South Island, we get this. So we see that by equal island, which is over here, this column. Now this becomes the index. So each row is the row is labeled with south because we have in island only one value and that's south. So the row is labeled south, and geometry is all these multi-polygons are merged together, and this is how it is presented in the bracket. And REGC 2020 underscore V is 12, 13, 14, 16, 17. So all these values. And REGC 2020 underscore 2 will be all these regions. So this is how it looks like. And we display REGC 2020 underscore 2 column south underscore island dot REGC 2020 underscore 2 gives the index for that row, which is south, and the REGC 2020 underscore 2 value, which is West Coast region, Canterbury region, Otago region, and so on. And the data type is object. We plot this south underscore island plot. So it looks like this. So this is the plot of the geometry. And yeah, so it doesn't, okay, so it shows all the polygons together. So it's geometry. And then let's look at the regions plot. So regions dot plot open and close bracket, we get this. So remember we have this path over here shown because the geometry is for each of those regions, and each of those regions are marked with this boundary. The white boundary, and that boundary is shown when the geometry is separate, and when the geometries are combined, that that is shown all together. So there is no boundaries for each region. They are all shown together. So that's the difference. Now next, we will plot the geometry of the South Island. So South Island dot location, and we'll put the in the raw label, which is south dot geometry, and this is how it looks like. Import Shapely, because now we will use Shapely. We'll pass this command. So prepared underscore geometry equals Shapely dot prepared dot prep of South Island dot location south dot geometry, and printing the prepared geometry. It looks like a command over here. So let's have a look. Now we had MMI data frame, and the geometry uh, MMI data frame is this, and the geometry, if we want to print only the geometry column, then we do type dot geometry, and we run that. We get all these data, and then we want centroid of this polygon. So let's look at centroid, and the centroid becomes just say point, just say dot, and the coordinates are given here for the dot. Then we display MMI, and there's two columns here, and there is index for each row, and the geometry is multi-polygon. And then what we do is, let's check what we're doing over here is we creating a new column called South underscore Island in MMI data frame, and that equals MMI.geometry.centroid. We apply it to open bracket lambda MMI underscore poly colon prepared underscore geometry dot intersects MMI bracket MMI underscore poly. So wherever prepared geometry intersects MMI poly, that's MMI poly is the geometry, the centroid part of it. Then it returns true, otherwise false. So lambda MMI underscore poly colon prepared underscore geometry dot intersects open bracket MMI underscore poly close bracket gives the function. So on passing this command, there is a South Island colon created, and we have the values are false and true. And there are 1006 observations with 3 columns. And now what we do is that we subset from this MMI data frame, we subset where the South Island equal true. And so this is how we do that. We pass the command MMI equal MMI, and in square bracket we have the colon equal true, and so this is the subset of the MMI, and it contains only the rows where the South underscore Island equals true, and there are 673 observations with 3 columns, and then we plot this MMI dot plot open bracket column equal MMI. So we want this column here, comma, legend equal true. And this is how. So we can see that this part over here, where there is a dark, where there is yellow, is having a larger MMI values, and Alpine Fault is from are located where these yellow regions are. So, and this is where MMI fault is quite large. MMI values are quite large, in between from 8 to 10. So, and the lowest MMI is in this south part, which is which is 3, from 3 to 4. And then as we go up, we see that the MMI value is increasing in this green part. But on this side where there is Alpine Fault, the MMI value is very large, which means the MMI, the intensity, the earthquake intensity is very large. Very large earthquake can come there, and as I think that nobody should live on this near to this Alpine Fault because the damage will be larger. So the best place to live is this part over here, very south, and this part on top, this part, and all this blue part, blue regions. This green and yellow and orange, these regions are quite dangerous. Okay, so we will continue in the next lab.